Hi everyone, welcome to your first remote learning flipped lesson. The purpose of flipped learning is that you can get basic information and then apply it to further phenomenon, simulations, anything like that. Now, when you do a flipped lesson, what you need to do is take notes on things that you find important. Then you'll work on the follow-up questions that are listed. So let's get started talking about momentum and the basics of collisions. We deal with collisions in everyday life, and some of the most common collisions are in sports. So next week, you're going to apply a lot of your learning to looking at how collisions work in different sports. When we talk about collisions, there are three different kinds: inelastic, elastic, and explosions. So I'm going to take you through each of them and tell you a little bit about what they mean. I'm not going to go into the math though, but you're free to look at the additional optional flipped lesson that is at the end of your assignment. Let's talk about our first type of collisions, which are my inelastic collisions. We see these the most when someone is catching something or in a tackle similar to something you'd see in a football game. So this is when two objects stick together after they collide. So let's look at this example. I have my pink ball, which is starting out with some initial velocity, and then I have my green ball, which starts as rest. When they collide, they're going to move together. So it's like they stick together. So their final velocity is the same for both balls. Now, there are two different situations we can have. The first one is at rest and the other thing is moving. However, I can have another situation where I have a ball that is moving and a second ball that is also moving, maybe towards each other. And we can think about this maybe in, like I said before, maybe a tackling situation where two people are moving towards each other and then they move away. But in all situations, they attach and then the final velocity is the same. Our second type of collision are elastic collisions, and these are a lot more common in everyday life. If I think about collisions maybe in a soccer field, when you're kicking a ball, when you're playing pole, when we look at a car crash, often it's going to be elastic collisions. So this is when two objects, when they collide, they are not sticking together. So they're bouncing off each other, for lack of a better term. Now, in this situation, we see that both of these have an initial velocity, but they are different. And then they also have a final velocity, and they could be the same, but most of the time they are different. Okay. Once again, we can have two situations. Maybe one object is at rest, and then the other object is moving towards it. Now, one important thing that I want to talk about is that the final velocity of each are different. And maybe they both have the same final velocity. However, what's different about these final velocities is for this purple ball, this one is negative. Now, as you do your simulation later, you may see that they don't always follow this pattern of bouncing back. Another option is that maybe this purple ball continues moving in the same direction. But the big part of it is that they don't stick together. They're colliding and then going in some different direction. Our last type of collision are explosions, which are technically elastic collisions because they are not connected at the end. So we have both starting at rest here, and then they explode in opposite directions. So we're assuming something is making them explode in the center here, okay? Like I said, technically an elastic collision, but because always my velocity initials for both are 0, we call it an explosion. We just went over the three different types of collisions. What's cool about collisions is that we can always predict the outcome. Why? Because we use a concept called momentum. And momentum is the effect of an object's mass and velocity. So for anything moving, we can figure out the momentum of the object. So momentum, our abbreviation is P. Why? We ran out of letters. And then that is a linear relationship, mass times velocity. Okay, so as mass goes up, momentum goes up, or as velocity goes up, momentum goes up. And you'll see that in your simulation a little bit later on today. Now, how can we tie in collisions and momentum? Well, we can do this with one of our really important physics concepts, which is the conservation of momentum. And in a few weeks, you are going to see this similar concept when we talk about energy. Now, the conservation of momentum is just saying, in a perfect situation, all my momentum before is equal to all my momentum after. Okay, so let's look at this example, and I'm going to prove why this always happens. So let's say that I have a blue train and a silver train, and I gave you the masses right here. My silver train starts at rest, and my blue train is moving towards it so that they collide. Now, they're going to move together at the end, so this is an inelastic collision. Now, let's figure out the momentum before, okay? So for our blue train before, remember I have momentum equals mass times velocity. My mass is 6,000 kilograms times 10 meters per second. So I'm going to get a momentum of 60,000 kilograms meters per second, okay? Now, my momentum for my silver train, okay? Now, I do have a mass, which is cool, but it is not moving. So I actually have 0 momentum. So before, I have a momentum of 60,000 kilograms. Now, since this is an inelastic collision, at the end, they combine. So let's see if this all matches up. So afterwards, same thing, I have my equation. Now my mass is now combined. Think about why it's combined. Well, because it's now one whole unit that is moving, okay? And 6 meters per second, okay? So if I do the math here, I'm going to have 10,000 kilograms times 6 meters per second, which, guess what, is going to give me 60,000 kilograms meters per second. So this is telling me something super important, that my momentum before is equal to my momentum after. So every collision, we can predict what's going to happen in a perfect situation. And as we know, yeah, there's some things that are lost because of friction, because of air resistance, all those things, but it is always the same before and after. So what you're going to do next, if you need to go back and watch different parts of the video or kind of skip through, it's totally up to you. Now you'll answer the follow-up questions, and after that, you'll open up that simulation to do some additional practice. Now, if you're someone who wants to learn a little bit more about the math, especially if you're taking AP Physics next year, there's an optional flipped lesson at the end that you are more than welcome to do.